Okay, and I see like our time limit has gone down, so it's nice. It started already. Okay. All right. So, relax after the last session. We're good. Let's talk about object storage, storing objects. And I know it doesn't really appear that I'm going to be talking about storing objects. I'm going to be talking about storing actual objects. And in the first example, we'll talk about ice core samples. If you're unaware of what ice core samples are, they are cylinders of ice that are drilled out of ice sheets or glaciers, and they contain a record. They provide us a record of the climate of Earth. The interesting thing for our talk about this is that this data, this columnar, I think the most columnar data that exists, it arrives at a storage facility that you can see on the right image, and this guy, he parses the data. And you can see how the scientific community that has an interest in these materials, how they choose to parse the data. And they parse these columns. It's really columnar store. You have your time series. Top is newer ice, bottom is older ice. And it's parsed to the different things that are interesting for the science community to research. In other words, there is a span of inquiry that the scientific community that's interested in this data has, and it's a characteristic that affects the parsing phase and the indexing phase. It's so easy and predictable to parse this stuff. It gets stored really compact, and it's kind of boring, right? It's on these shelves. Let's take, for example, a scientist arrives. You kind of already know what they're going to ask about, so you pre-parsed things in a nice, comfortable way. And let's take for a kind of a science fiction-y kind of take on it. Let's say lots of scientists are coming to query at the same time, and you took that column and you said, well, I want more people to be able to look at this data. I just want to cut them all in half and re-index them. That's really easy to do. It's like super easy. The middle is just the time divided by 2. Let's take those shorter columns, add extra shelves, and now we've re-indexed the data really fast. You could probably do it. Like if someone said, this is what we want to do, cut it in half and restore it. It's practically easy to re-index the data. Let's take a look at a different type of object storage. And you must be thinking I'm going to look at S3. No, other objects, like in a museum, okay? If you are working in a museum and someone comes up with an object and they said, you don't know what it is, but I need you to index this into the museum. There's absolutely no idea what they're going to come up with, right? It could be an archaeological artifact. It could be a painting, a big statue. It could be dinosaur bones or a massive postmodern installation of, I think it's like the Kraken or something in pink. So you have no idea what they're coming up with. And the neat thing about museums is they do catalog things. So there is an indexing process. It's just much bigger. Like the index is much more complicated. The indexing process is more complicated. We don't know what the span of inquiry is huge. Someone coming to a museum might have a question about anything, like what are the n biggest objects in the museum? And it might be these two, you know, even though they're from completely different fields. If, for example, take our previous example in the ice storage, lots of people are coming to the museum and we want to be able to answer their queries quickly. Can we easily manipulate the museum by taking a piece of each installation, of each exhibit, and make a little mini museum? That's really hard to do. It's hard to figure out how we would go about such an action. So taking the data and re-indexing it or moving it around in such a way that makes sense and scaling it out is much harder when we don't know what the span of inquiry is. And very similarly in OpenSearch, we can scale OpenSearch. Also in a museum, you could add an extra wing. Scaling OpenSearch means, horizontal scaling that is, adding an extra node or removing one. So it's simple to do in action. However, it's not just that. So if you want to scale the load, okay, you want to scale the and make your cluster be able to handle an even amount of load with more nodes, it's not just adding extra nodes. And we're going to talk about that today. This is me. I'm Amitai Stern. I'm a member of the OpenSearch Technical Steering Committee, and I am the team lead of telemetry storage at Logs.io. We manage a couple dozen OpenSearch clusters, which contain, I think, around a couple of petabytes of data, of logging and tracing data of thousands of customers worldwide, in addition to Thanos and M3DB clusters where we store metrics data. A benefit I wish for you to have gained from this talk is some more clarity about scaling OpenSearch so that you can actively plan for it rather than be unpleasantly surprised. And maybe also some intuition towards what it would take to implement autoscaling. And we have to start with horizontal scaling. Every database that's distributed has this thing called horizontal scaling in some way or form. And the reason we're going to have to do horizontal scaling is because the database changes. Queries can get heavier, and we need more CPU power to calculate things. You could be running out of space because more and more data is coming in, so you need more disks. You might need more memory. Some of the nodes, which I'm going to use in the rest of the talk as these sort of rectangles, some of the nodes may fail, and other nodes need to take over the workload of the failed node. So scaling is going to happen. And there's an expectation. When we scale horizontally, we expect, if we had one node and we scale our cluster to 10 nodes, our expectation is that miraculously it's going to be able to handle 10x the load, right? That's what we expect. But adding the nodes does not do that. Adding the nodes is just adding more machines. What we have to take care of is spreading the load across. We have to make sure that we're evenly spreading the load across all the nodes, and only this way are we going to be able to get the horizontal scaling we're looking for. If there's a disproportionate amount of load on one of the nodes, we call that a hotspot. How many of you have encountered a hotspot managing clusters? Oh, wow, more hands than I expected. Yeah, so many. The way we distribute the load on ingest, we'll talk about ingest and then we're going to go over other examples. When we index the data, we don't just randomly send things to different shards, okay? And you can think of a shard as like a little database. So the index is controlling like little databases, and that's how we want to distribute the data. And the way a certain document is going to arrive at a certain shard is hash mod n being the number of shards. And this is good because we can retrace our steps and we can find that shard, that document, sorry, in the particular shard. In this example, like hash mod n leads us to shard number 1. Okay, so our document goes into shard number 1. Let's say, just for the sake of argument, there's a lot of data coming in and we want to scale out horizontally, and we want the index to suddenly have another shard to handle the extra load. If we would stick around with hash mod n, we'd be in trouble. And it would go like this. The document that we stored is in shard number 1. We just added another shard. Hash mod n is the wrong calculation because it's n plus 1. And so if we do our hash mod n, we're going to arrive at shard 0. And shard 0 does not contain the document. So we can't just, it's kind of a difficult thing to change the way we index the documents in order to be able to scale out that flexibly, that dynamically. Other data stores do enable, they have what's called consistent hashing and different types of hash rings, and they enable us to be a little more dynamic with extending the bounds of an index, or actually the resources an index has. So we don't have that in OpenSearch. In OpenSearch, we have a fixed number of shards, and that's how things are for now. Okay. Yes, we can implement changes, and we could maybe decide that one day we want to be able to be dynamic. It's going to be much more complex. So for now, for the talk, and probably for the next year or so until someone developed this, we have a fixed number of shards. Sometimes horizontal scaling is easy, okay? And much like a piece of cake, it has a cost. So we'll talk about the different times when it's actually rather simple. And in these cases, you might think implementing autoscaling is simple. And we'll see when it is and when it's less. So the really easy one, this is the best example of easy autoscaling. When our resources are spread out evenly on all these nodes, and we have, let's say, 4 nodes in this example, and we don't have enough resources, let's say, for the disk space, one of them, like one of the resources needs to grow, or all of them, then we just add another node. So if it's disk space, things are super easy. And the good news is if you want to implement autoscaling for scaling out for disk space, it's easy. You have to have a few settings to make sure that you're not going to get a hotspot on the new node. This is true. Talk about that in a second. But just adding the new node means that OpenSearch will automatically start allocating shards and spreading them around. And shards might not be the same size. And the shards that are going to be spread around might all be shards that you're writing to at this very moment. So easily you'll have a situation where 100 shards are going to be on each node, but the 100 shards that landed on this new node are really tiny. They're like a megabyte each. Or those shards are being written to at 100,000 documents per second, and then that node is impossibly overloaded. So ways around this are, one of the ways would be dummy shards. You add a bunch of dummy shards that don't have anything on them, and they're allocated specifically to this node, and you just remove them periodically. You have a script just like takes a few off every now and then. And then slowly but surely the load kind of evens out. Another thing you want to make sure is that your shards are more or less the same size, because if they're not, then you might have that first situation we described. So daily indices are okay, but not great. Another setting you might want to use is total shards per node setting, which is on the index level setting. And that way you can say each index can have at most 2 shards per node, and then you won't get a situation where one index gets completely poured into this one shard. So those are ways that scaling out is relatively simple. The problem is when we want to kind of scale back in. So in certain cases, if the entire load on each of the nodes is rather low, scaling in is easy. However, there are multiple factors normally that affect the load. So if we only look at the disk space, autoscaling in this case might be a mistake because we may fail to see that there is, let's say, 20% disk space on each of these nodes, which is bad. We're wasting money. We want to reduce, let's say, one of the nodes. If we do so, what might happen is the indexing load, the write load, on the remaining nodes might be too much. So if everything's okay and the load is similar on all the nodes, we're good. And you can actually scale in by excluding the node, and then it goes down to 4. So this is where things are simple. And they're still not that simple, right? You still have to understand when you're scaling in, it's tricky. What is the load on each node? Is it the disk? Is it what's going on with the writes? What's going on with the reads? And if all 3 are below some threshold, then you'll say, okay, there's wastage here, and we maybe want to remove one of the nodes or 2 of the nodes. So automating that is possible, a bit tricky, but it's possible. Other cases are much more complicated, and particularly it's when you have indexing that goes up and down, and they're writing a lot more during the day and a lot less during the night. And this is where I get the most inquiries doing my job, and someone's like, at night, they're not sending anything. Why do we need 20 nodes in the cluster? Just reduce it. We only need the disk space. In the day, they're sending a lot. Increase, in advance, using sophisticated machine learning, understand the patterns of randomness in indexing, which is impossible. And especially when you're multi-tenant. So let's take the example of just like a night-day thing, okay? And just roll with it. Let's go with the example. We have an automation that looks at the indexing rate, and it says the indexing rate is a night-day. We know this. So what we're going to do is we're going to scale for that. All right, it's like noon, let's say, around right now. 2 o'clock, it starts to get a bit high. People are working more, they're after a few coffees, they're getting back from lunch, and it's really getting to be too much. So what we want to do is add more shards. And the way to do this is a rollover task. So you create a rollover task, and you add an extra node, and the new index has more shards. Is there a downside to this? Not really. If our index already had 9 shards, the complexity of searching over 9 shards or searching over a read alias of 5 plus 4 shards is the same. So we don't have to worry about that. And our indexing is OK. We're good. We do have a little bit more shards, though, than we started with. Around 8 p.m., everybody's already gone out of the office. The indexing goes way down, and we're wasting money again because all the compute, nothing's happening over there. And we want to reduce the size of the cluster. So let's assume that each of these nodes are getting like 20% of the load. What happens when we reduce one of those nodes is that one of them is now getting 40%. So we have a disproportional amount of load going to one of the nodes, which causes a hotspot. What do? Our automation sees this. It goes, oh no, I'm going to roll over the index again. And now we have, and it's OK, now we have this new index. It's got 4 shards, and it's perfectly spread out. And I'll just take a moment to say that the best way to avoid hotspots is to be perfectly spread out. And I don't mean that you need 1 shard per node, but you need an even amount of shards per node. And this means you're going to have an even load per node, which means no hotspots. It's easy. So if you're trying to avoid hotspots, just do that. The problem is, look how many shards. This was 1 cycle, night, day. And we more than tripled the amount of shards that we had. And those indexes might be really small. Like each shard might have 5 gigs each. So there's a lot of waste here. We could have a background task that starts merging them. There's other ways to get around this, but it starts to get really complicated. What happens if you have a customer that's just going up and down all day? They have an exception, they fix it, then they think they fixed it, OK? They fix their problem, they redeploy, they didn't fix the problem. So everything goes up again, and you have the same night, or, up and down kind of process. So automating this, it gets really tricky because you're going to have to deal with the overhead of shards. The problem with having so many shards is that the cluster starts to get unstable. It has to maintain the state. It has to understand where all the data is, where each shard is. If we want to do a reallocation, you have to figure out how many shards we should move where. It becomes really difficult once you start to hit thousands of shards per node. And I'm not advocating for 600 shards per node. I don't know if you read different documentation that says 600 shards per node, each shard between 10 and 50 gigs. You don't have to. It's up to you. Your use case may be great with a terabyte per shard and, 2,000 shards per node. It's whatever your use case, you have to figure that out on your own. But you will get to too many shards in this case. Let's start to talk about a little bit about solutions for this, and which is great because I should be hitting the middle mark, and we're good. OK, so the way to kind of work around this manually is you kind of the real simple one is to overshard your index ahead of time, and then when there's load, you hulk out. You just double the size of the cluster, and the shards just spread out. OK, so this is one way to fix this problem. Is you're already oversharded, or as Bruce Banner, always angry. So you're always oversharded and ready to do that. The problem with this is that you get tons of shards still, and also it's very hard to calculate the sweet spot between the right amount of shards when you overshard and not having too many shards. So we don't want many small shards, but on the other hand, we don't want too few because we do want to scale out. And things get even more complicated when you do multi-tenant clusters because some customers spike, but not as much as others. OK, so it is a good idea, but not exactly the way it is. So I'm going to give 2 examples of sort of solutions that work this way. They're going to use the same concept. However, a little bit different. So the first one is called a burst index. And what we could implement is you have your data stream, and it has 2 heads. It has a slow head and a fast head, or a burst index and a regular one. And the way we write, we only write to the regular one normally. If we expect a burst, we spread out. We add nodes, we spread out the burst index, and we switch the right alias. And this will work individually for each one of the tenants. It is kind of a cool way to do things. It kind of looks like this. So we'd have different box types. Box type is a arbitrary label you can give a node. So we'd have, let's say, low box type for the normal nodes. And we'd have write alias on the green shards. So those are being written to when we have low throughput. Throughout the day, we'll get not so low throughput. Things start to get heated up. And since we expect, because we're looking at a pattern of night-day, we're expecting maybe we're going to have to burst. So we add these burst nodes. They're smaller nodes. We're not going to store a lot of data on these. They can be smaller. We just need the compute. Okay? Since the red shards, the burst node shards, they have a setting in their index setting that they're supposed to be on box type burst or low, and at this point they start to spread out. So we can automate that as well. Just by adding the nodes, they'll automatically spread out. And then by the time we have high throughput, it's going to go to all of these. Later on, it might go back to not so low throughput, and we can remove those shards. Remove those nodes, and then bring them back into the other cluster. So we do still have extra shards, all right? But the good thing is we're only looking at the write phase. This is not the index that we're working with for a while. We're only looking at the head. Okay, so every now and then what you want to do is a rollover and merge. Okay, so that's when you're on low throughput, you roll over merge. This way it's kind of like a zipper. You know, you have like the two ends going into one, and one of them is like much smaller fine-tooth zipper. Okay. Another option, and this other option is particularly when you have a lot of bursts. So you have different customers or different data streams being sent to the same cluster or to many clusters, and each time, in any given hour, someone is bursting. There might be a spike. Maybe it's not night day. Maybe it's just any time of the day someone's going to spike, and you don't want to have to be stuck trying to figure out, which box type to use per customer. It really gets complicated. So another similar idea is to maintain what we'd call a burst cluster. So in normal behavior, you're sending everything to a certain cluster, and when one of the tenants bursts with like a ton of data and the ingestion goes up, you would move it over to your burst cluster. And that would look something like this. If each of these clusters have that number of nodes, on each of these clusters, we'd guarantee that every single index has that number of shards, or a multiple of such. And then that means that there's no hotspots on them. If one of the tenants starts to spike, what we can do is shift the ingestion to go to the burst cluster. And in this case, we have tons of nodes. We have an index prepared over there for them, and it's indexed really quickly. In this case, tenants suffer from nearly zero lag because the data is just going from one cluster that's capable of handling the load to another, which is capable of handling like much more. The indexes on this one are going to be much smaller, and we can handle momentary bursts this way. Of course, we have to implement cross-cluster search in this case because you're putting data on two separate clusters, unless you're using OpenSearch dashboards, which is kind of a single pane of glass. And then you could search, but you'd have to handle your aliases. Cross-cluster search can really make this a more simple solution. In other cases, two different clusters are going to spike at the same time. You can send multiple streams to the same big cluster. And you may think, well, in the meantime, this cluster is wasted, 60 nodes. Like, that's such a waste. So first of all, they could be smaller nodes. And second of all, you can put accounts or customers or data streams, whatever you have going there, that are always high throughput. You could always put them there, and that's where you manage them. So in other words, you could have tiers of throughput. You have low throughput tier for data streams that are low throughput, and if they change their throughput, you open an index in a higher throughput tier, and you keep moving them around. Eventually, we're going to incur a bunch of garbage because there's going to be indexes all over the place. And we're going to have to move things into S3 or some object store and then restore it and merge. And this process is going to have to be done on the downtime or in some separate time where things are nice and cool. And so these are two topologies which are neat, and you could use them or implement them yourselves. It would be cool if we could have that in OpenSearch, just something that works that way. It would be kind of hard to have the last example out of the box. And so just to summarize, we have different resources that we need to scale. The load on our clusters is not just one thing, it's several things. our nodes combine read and write, right? It's a shared resource. So you have to understand what is the load that you are trying to spread out when you scale out. And when you're scaling in, do all the different loads that you have on the cluster, are they all able to scale in? And this is the main reason why autoscaling gets really, really complicated. We took a look at these two solutions, and you can implement them. But I think only the second one might be an ISM, because we have the ISM plugin. Maybe we could do that over there. And as we saw, like a simple, add shards, remove shards, add shards, remove shards is going to put us in a pickle. So not a great solution. But we can work around it. And you see that it really matters what your use case is. In certain use cases, the hulking out kind of index, the oversharded index, is perfect. And you don't need to go further than there. So you really need to fine-tune it to your own use case. Should we have autoscaling? Autoscaling is awesome. Do you want autoscaling in OpenSearch? Just start adding nodes on random without your control. Just happen. AWS bill growing and growing. No? OK. So we really should. I believe so. Like the system should at least be autoscalable easily. So it should be just I want or don't want autoscaling in my cluster. That should be the way it goes. And there are different. I took this is like the last slide I added last night, because there's different initiatives that make it maybe the future much brighter. So if we separate read and write, then things get really easy, because you could say the load is over here on the ingestion. I'm controlling it. It's auto-scaling based on that. Whereas the disk, it's all the search. It's over here, and I can scale the disks based on that load separately. And that's where things start to get really interesting. So that's my talk. And open for Q&A at this point. Thank you.